Welcome to this second lesson of our Path Control e-learning module. It is now time to demonstrate some of the path control mechanisms we discussed earlier by configuring them in real routers and network elements. We will configure from a task-oriented perspective. In other words, let's try to identify the scenario objectives first, and then lay out a plan to use the tools, configure the solution, and verify the results. Let me tell you about our screen layout here. We will use the bottom of the screen for our router and device consoles. Most of the demonstrations will take place here. Notice that we have multiple routers and devices in the same lab, and we will move between them by using these tabs that you see. In this example, we have routers R1, R2, and R3. We will use the top left panel to display the lab topologies. This includes IP addressing, Layer 2 and Layer 3 topologies. In fact, this is the topology for our current demonstration. We will use the top right panel to display additional information needed, diagrams, and command syntax. Let's get started. If you look at the top right panel, you can see that we will demonstrate these two scenarios. First, redistribution with multiple edge routers, which is a classical case that might result in routing loops or suboptimal routing unless some form of path control is defined. The second scenario will take us through configuration of adaptable routing based on tracking of network conditions using Cisco IOS IP SLAs. Now let's start with our first scenario, path control and redistribution. Routing protocol redistribution with multiple edge routers represents a challenging scenario for multiple reasons. The first thing to think of is that redistribution is a process of translation. In our example here, we have the Open Shortest Path First, or OSPF, protocol, and the Enhanced Interior Gateway Routing Protocol, or EIGRP. They are very different. The metrics are different, the administrative distance is different, and the operational framework is different. It almost makes sense that the result of translating one to the other might be messy. The second issue we have is multiple exit and entry points to and from each routing protocol domain. What happens is that routes are injected back and forth between the domains, increasing the likelihood of routing loops and suboptimal routing. In our particular scenario, we have R3 injecting routes, specifically 192.168.254.0, into the EIGRP autonomous system. The first redistribution point is R1, which translates that advertisement into OSPF, with an adjusted seed metric that makes sense for an OSPF network. The problem is, the now OSPF-looking advertisement is translated back into EIGRP by router R2, and the resulting metric is better than the one advertised by router R3. Now, R1 thinks that the best path into the external network is via R2. There's something wrong here. Look at the resulting routing loop caused by suboptimal routing. This is very difficult to identify and very likely to happen with default settings. How do we fix this? The general strategy is to prevent known routing information being fed back into the source domain. So routers need to say, if the route originated in EIGRP, do not advertise it back into the EIGRP domain in order to prevent routing loops. There are multiple methods to accomplish this. Some of them are listed here. As shown in this example, you could try to redistribute dynamic routing information in only one direction, OSPF into EIGRP, for instance, and use static or default routes from the other direction, EIGRP into OSPF. This gives you more control of what you are advertising. By summarizing all EIGRP routes in the form of a default route, you prevent specific destinations being advertised back into EIGRP. The second suggested approach is to implement route filtering, perhaps using distribute lists on R1 and R2, or, better yet, prefix lists for better identification of subnet masks. With this approach, you can deny the advertisement of EIGRP routes back into EIGRP. The third method is commonly used to identify specific redistributed routes within each domain. Route tagging can mark the route advertisement by using route maps and can identify the tag in multiple places of each routing domain, especially at the edge routers, where you want to filter those tagged routes to prevent the routing loops. We will demonstrate the configuration of the third strategy, namely route tagging. We will then filter those routes in the return advertisements. This is how it happens in our particular scenario. R3 injects 192.168.254.0 into EIGRP. The route is redistributed into OSPF and then marked with a certain tag on R1. R2 identifies the tag and removes the advertisement on its way back into EIGRP. This prevents the suboptimal path from being learned in the EIGRP domain. One of the advantages of this strategy is that the specific destination will show a tag when being advertised in the OSPF domain. This allows you to implement a specific routing policy for that destination in that domain by simply matching the tag. To accomplish route tagging, we will use a specific set of commands. This reinforces our premise that path control is not a single feature, but the integration of multiple commands and Cisco iOS components. The tools of our trade in this particular scenario are as follows: prefix lists to identify specific prefixes, as well as access lists or other identification tools. However, prefix lists allow the flexibility of matching not only the prefix, but also the mask included in each advertisement. Route maps will facilitate the action of tagging. Remember, route maps allow you to match the prefix using the prefix list, and then add a tag to the route advertisement using the set command. Redistribution needs to be there because we want to provide end-to-end connectivity across both domains. But this time, the tagging process will control the redistribution command. As usual, the use of show and debug commands allow you to verify your configuration. In terms of specific configuration steps, here's what we will do. This is guided primarily by our strategy and by command precedence in Cisco iOS software. Notice that this list follows our overall strategy. In Step 1, we will verify the base scenario. In Step 2, prefix lists will identify specific route advertisements. Step 3 includes route maps, which will help us do route tagging and also match tags. In Step 4, the route maps should be attached to the redistribution command in order to control the redistribution process according to our strategy. Verification commands follow to test and confirm the intended routing protocol behavior. Finally, additional tests will verify that the changes are working effectively. We will detail our addressing topology and perform these steps to the end. This is our specific subnetted addressing topology in the left panel. You can refer to this diagram by looking at this panel at any time during our discussion. Notice that the external routes in our test network are 192.168.253.0 and 192.168.254.0 at the bottom. Both have 24 bits of mask. The EIGRP network includes direct connections between R3 and the other two routers, and an additional link between R1 and R2, the 10.3.7.0 network. In this scenario, you will see how this particular link is the source of our problems in feedback routing information. There is also a similar link between R1 and R2 in the OSPF domain. Our first step is to verify the base scenario. Let me start by using some of these commands on R1 to display the status of the redistribution process. Now, let us move to the bottom panel and start demonstrating our scenario. The show IP route command is probably the best source of information to learn how routing is being accomplished. Remember, you can display the routing table for specific entries by simply adding the prefix that you are trying to investigate to the end of the line. In this case, we are going to investigate the 192.168.254.0 prefix. We are learning it via the Fast Ethernet 0/1.2 network or interface. This means from R2 at 10.3.7.2. Now this is a real problem. We should not be learning this network from R2. We should be learning it straight from R3. Learning it from R2 will create suboptimal routing. Another good source of information is the show IP protocols command, which tells us how redistribution is taking place. In this example, we can see that for EIGRP, we are redistributing OSPF. Also, for OSPF, we are redistributing EIGRP. In the end, a trace route will tell us how we are getting to the 254 network. So let's just trace the .1 host on the 254 network. I'm going to use a time to live, or TTL, that is high to show that we have a big loop that goes back and forth between R1 and R2 on that 10.3.7 link. Now, we seem to have two problems here. One looks like a metric problem that leads R1 to R2 to get to the subnet 192.168.254.0. We can quickly verify this in R1 by showing the EIGRP topology table, and we can do it for the exact subnet that we want to investigate. This is a very good command because it shows you the two ways we have to reach that network. One is via the 10.3.7.2 router. That is R2 on the 10.3.7 link between R1 and R2. Let's look at the metric there. The feasible distance is a 5-digit number. Now, look down here at the other way to get to that network, via the more natural path, 192.168.2.2, directly via R3 on the serial interface. But look at that metric. It's higher. So it's definitely a metric problem that is leading R1 to R2 and the suboptimal path. This looks like a symptom and not the source of our trouble. So, let's go to R2 and try to investigate there. We will first see how we are getting to the 192.168.254.0 network from R2. Now, look at that. We are seeing it via OSPF, which is also suboptimal. It's not directly through R3. Not only is it going through R1, but through the OSPF side of R1. We have the next hop here, the 10.2.7 network. But look at this. When redistributing that network from OSPF into EIGRP, we have some seed metrics going into EIGRP that could be the source of the metric's symptom. When injecting the routes into EIGRP, someone created SID metrics, which is a best practice, but it could lead to suboptimal routing if those metrics are better than those advertised by R3 toward the same destination. Should we change those metrics? Well, the source of our problem isn't really metrics. It's the fact that the 254 network is being advertised into OSPF and then back into EIGRP. That's why R1 is getting confused, and the trace, if we go through it again, shows an infinite loop. To illustrate, look at the top right panel. Our critical networks 192.168.254 and 192.168.253 are being reached via the 10.3.7 link. This is because R3 advertises into R1. Then R1 redistributes the routes into OSPF, and R2 picks up the advertisement and it redistributes the routes back into EIGRP. That is our loop. Let's fix this. Remember, we're using a route tagging and filtering strategy. So, our first step is to configure the prefix lists to identify the offending route advertisements, namely 192.168.253.0 and 192.168.254.0 networks. Let's create the prefix list on R1. You can see the description of the syntax listed here in the top right panel. Notice that this is a partial description of the command, specific to what we are trying to accomplish here. The prefix list command is very powerful and has many available parameters. In our example, the LE32 keyword identifies any mask with a length less than or equal to 32 bits in order to identify the prefix and any smaller subnet of the prefix with a different mask length. Notice that we are also creating two lines for our prefix list, one for each network that we are trying to identify. Now we need to apply the prefix list by using route maps that define actions for the identified prefixes. Remember, our action here is to tag those prefixes. The route map has a specific structure and there are several options. The syntax shown here in the top right panel is partial and illustrates only the options that we are using. As we create the route map in R1, remember the use of route map sections and how they are evaluated in order. The first section in this example is section 10. We need to match routes according to our prefix list. So it's match IP address, prefix list, and then external, which is the name of the prefix list. Then tag them with a certain value so that they can be identified in R2 later. We will use tag 1000 for this example in this set command. This has to be done on both edge routers. Remember, route map sections or sequences are evaluated in order, and they function similar to an access list in that there is sort of a deny any implicit section at the bottom of our route map. In this example, we are not trying to deny anything. We are trying to tag prefixes. In fact, this is why our section 10 has a permit keyword. So we need to add an empty sequence or section at the end of our route map to prevent unidentified prefixes from being filtered out. We do it and call it section or sequence 20. Same syntax, same route map name. So, it's the same command, same syntax, and same route map name with a different section number. It is somewhat like a permit any if we compare it to an access list. I type exit and it is empty because I want to match any prefix. I don't have a set command because I just want to permit the prefix redistribution process. The first route map tags routes, but we need another one to identify the tag and filter those routes. The reason for this is that the first route map will identify the route advertisement into OSPF, in this example at the top right panel on R1. The second route map will match those tags and then block them on the other edge router R2. Of course, knowing that both routers could be doing the same job at any given point in time, router R2 will need to have a similar configuration. One route map to set the tag before the route is advertised to OSPF, and then the other route map on R1 to match a tag and deny. So, both routers need both route maps. We will call the second route map match tag. Notice how, this time, our first section performs a deny action for prefixes that are tagged with 1000. We need an empty section at the end to make sure that all other routes are allowed. That's why section 20 has a permit keyword. Next, we need to configure the route maps into the redistribution command syntax shown in the top right panel. We will start with OSPF. So, it's router OSPF 1. We simply define the same redistribution command that we had in this router previously, but then attach the route map in the OSPF direction. We are going to use the set tag command or route map to set the tags. In the reverse direction, we are going to go into EIGRP. Type the same command that we had for redistribution. Notice that this one seeds the metric for EIGRP's 5 composite metrics, matches externals for OSPF into EIGRP. Then, once again, we are going to attach the other route map, match tag. So, we are going to try to identify the routes on their way back into EIGRP and then block them. Both edge routers could cause routing loops because both are involved in the redistribution process. So, we need to do the same on router R2. Let's quickly replicate the configuration there. First, the prefix list. Notice that they are identical. Next, our route map that sets the tags for advertisements into OSPF. It is also identical. Next, the route map that denies advertisements tagged with 1000. Here it is. And finally, we attach the route maps to the appropriate protocols. In this example, OSPF and EIGRP. So, R2 is configured. As you can see, we have attached the route maps to the routing process using the redistribute command, which is shown at the top right panel along with its syntax. We did that in both edge routers, the redistribution points. Now, how can we verify that all of this happened? We use the show IP route command, which is at the top right panel along with its syntax. In R1, we use the show IP route command. We now see that the critical networks 253 and 254 are reachable directly via R3. We can tell by looking at the advertisement points. 192.168.2.2, that's R3. Notice when you use the show IP route command with the specific prefix the way we've done it now, the output shows how the redistribution process is now scoped within the action of our route maps. It's redistributing via EIGRP and OSPF, and advertised by OSPF with a route map of set tag. Surprisingly enough, other than the show running config command, our source of information, the show IP protocols command, does not display the route map information in the lines referring to redistribution. We can also check the configuration objects by using specific commands. For instance, the show route map command displays the configuration of the route maps that we created. This is very good, but nothing should be considered final until we verify the routing loop is no longer there. So, let's try to trace again the problematic networks. Look at that. It's reachable via R3, which is optimal, and there is no longer a loop. There are also other ways to verify this. In R1, if we use the show routing table command and use a very useful parameter called section to filter, we can see that the 254 network is being learned via R3. Now that we know we are learning it via EIGRP, if we display the topology table, show IP EIGRP topology, and filter to the critical network 254.0, we can tell that there is only one successor now, and that successor is via R3. We are no longer learning it from the loopback via R2 on the 10.3.7 subnet. That is because we are filtering feedback advertisement from EIGRP sources into EIGRP again. Now, what happens if the serial link between R1 and R3 goes down? Are we going to use the alternate paths? Sure, we are still learning the network from OSPF. Let's prove that. Obviously, it will not be in the routing table, but if we display the OSPF topology table or database, which unfortunately doesn't use the topology keyword, but rather the database keyword, and perhaps filter to 254, we can see that it's there, and we are learning it from OSPF. In fact, do you recognize that 1000? Yes, it's our tag. In fact, there are better ways to display this and display the OSPF database only for external routes, and then filter to our 192.168.254 network. This is a great way to look at specific parts of the database. We are seeing that the link state ID, our network, is being learned via OSPF, and here is the external route tag 1000. That command again was show IP OSPF database using the external keyword and then filtering to our network that we want to investigate. Now, is our route map really what is tagging the network? Well, the show route map command doesn't show statistics. We have our set tag route map here, and even though it shows what looks like statistics and packet counters, they only work with policy routing, or when you apply the route map as a policy routing tool, but not for redistribution. We can see that we are filtering to the prefix list external, and that's something we can display. And since it does have counters, we can do show IP prefix list detail external, and that's going to display the detailed counters. The detail keyword displays counters. Without it, the router would not display them. See here? That's our two networks that are a part of the prefix list. We knew this, but there is a hit count of how many times the advertisements have matched those networks. The hit count is up to 2 right now. Perhaps the only way to re-tag them, or have the route maps tag them again, is to clear the IP OSPF process. And of course, you should not do this in your own production network. It will take your neighbor adjacencies down. But for the sake of this exercise, it's going to work perfectly. If we clear that process, obviously the neighbor goes down. It will come back again in a few seconds. The neighbor is now at a full state again, and now it will look at that prefix list. Now the hit count is at 3. The network was matched, and because it's a part of our route map, it was tagged again. So, we are in fact tagging, and that's what's allowing us to deny those network advertisements. Let's debrief. What did we accomplish? Well, by using filtering mechanisms with a combination of prefix lists and route maps, aligning with our redistribution process, we were able to stop the feedback loop that was causing redundant and suboptimal routing information from being fed back into our routing protocols. Now, R3 advertises into EIGRP, as you can see in our top right panel. R1 redistributes routes into OSPF like before, but tags them with a certain value. R2 redistributes back into EIGRP, but filters tagged routes to prevent the loops. In looking at our configuration, the bulk of it is based on route maps. Let's just display our final configuration. Let's display a section of the running config based on the names of our route maps. So, we will display the configuration that sets the tag. Here's our route map. We have one route map for each direction, one that sets the tag and one that matches the tag. Here is the one that sets the tag based on our prefix list external. Setting the tag for that one and allowing everything else. We apply that one to our redistribution of EIGRP routes into OSPF. Our match tag is the one that matches the tag and denies it. So, if we display that one, we have a different route map and it's called match tag. It denies anything that matches tag 1000, permitting everything else. That one we are applying to the redistribution of OSPF routes into EIGRP. Here's an alternative configuration in our top right panel using the same route map tool. It uses only one route map for both directions. It would apply to those cases in which you want to tag all routes coming from the other routing protocol domain, not just the ones I had you identify in the prefix list. That's why we don't see a prefix list in this example. This alternative configuration is cleaner and less cluttered. It is also intuitive. The route map here, called tags, simply says, if the prefix is tagged, deny it and do not inject it back into the original routing process. If it is not tagged, then tag it because it is the first time we are seeing it. Notice that we are applying the same route map tags to both redistribution processes. So this is cleaner and keeps the configuration simple. So, what did we learn? Well, multiple tools are available for your path control strategy. The combination of those tools allows you to implement it. In our example, we used prefix lists, route maps, and redistribute commands to accomplish our goals. Part of our problem was the introduction of asymmetric routing by the redistribution process. We worked toward taming or mitigating those asymmetric routing effects. However, in general terms, asymmetric routing is not inherently bad. and tight control of this condition may be counterproductive. Keep it simple is the name of the game. We saw how our configuration can be tuned, reduced, and made more structured and intuitive. This helps in change management and operations. Tuning the configuration requires overall understanding of the tools we're using. For instance, remember that route maps have an implicit denial at the end. If you don't anticipate this and act accordingly, you could be denying and filtering route advertisements. So, suboptimal routing is not always easy to predict or identify. In our example, the result caused loss of connectivity because of the routing loop. Rest assured that you will hear users complain about this. So, we resolved our routing loop, but remember our initial concern was suboptimal routing. We still haven't resolved that. Let's treat that as a follow-up scenario to our routing loop demonstration. This time, we're going to use the administrative distance to resolve that issue. We will start at router R2. So, let's go to R2 and let's look at the routing table for our critical networks. The path toward the .254.0 network uses the OSPF domain via R1 as the back door to reach those destinations. Here is the interface, and here is R1 on the 10.2.7.0 network up there. In fact, if we trace the 254 network, we can see that it's going through the 10.2.7.0 network into R1 and then reaching R2 via the serial port between R1 and R3. But why is this happening? Let's compare the routing tables of R2 and R1 only for that one problematic route to 192.168.254.0. On R2, it's clearly going through OSPF as an external route. But remember this number, 110? This is the administrative distance of OSPF. Let's see what happens at router R1. In R1, we do the same thing and display the entry for the .254 network. We're using EIGRP and learning it straight from R3. Look at the administrative distance. The number is 170. If you look at our top right panel, we can illustrate what is happening. R2 learns about the critical networks in two ways. First, via R1 advertisements on the OSPF domain, and because of redistribution. That's the green line up there. Secondly, and using a dotted red line, R2 learns those networks from R3 via EIGRP advertisements. At that point, because it is learning from two different routing protocols, it applies basic administrative distance rules to select the best path. Those rules say that OSPF has a better administrative distance than external EIGRP routes. You can see our table here, 110 versus 170. That is why OSPF wins and the suboptimal route is selected. If we want to fix this, and we should, one available method is to change the administrative distances for our selected prefixes to change the default preferences while allowing for a dynamic and resilient environment. In this example, we can use the distance command to change the preference of an external or redistributed OSPF route. This includes the advertisements of routes coming from R1 that are causing the issue. Let's do this and see how things change by enabling the debug IP routing command. You should be extremely careful when using this command in a production environment. It's actually not recommended. Let's do this in R2. We need to do this in our OSPF routing process. Look at the syntax of the distance command in our top right panel. See how, with this command, we are changing the distance of OSPF external advertisements to 171, 1 unit above the default distance for EIGRP external advertisements. Now, as soon as we do this, the output of our debug command will tell us interesting things. One is that the 192.168.254.0 network has been deleted from the routing table. Soon enough, it tells you that it's been added again. In fact, the command is very useful. It tells you that there is closer administrative distance for that network, and that's why it's flushing the old entry and it's adding a new entry via the EIGRP network with a distance of 170. We can quickly verify that by displaying our routing table, only for that one section that includes our network. Now we are learning it via EIGRP and can see the administrative distance of 170. A trace will determine and demonstrate that we are in fact reaching that network straight via R3, and we are. We're going to need to do this also in R1 as the other redistribution point. So, we just go into our router OSPF configuration mode and define the distance of OSPF external routes to be one more than the EIGRP routes, so that the EIGRP is preferred for external routes. With this, as you look at the top right panel, the subnets are going to be advertised normally through R1 and R2, but the directly connected R3 is going to also advertise into R2. Now, we change the administrative distance, and the EIGRP route is preferred. And that's why EIGRP wins now. Another quick test, this time from R1, demonstrates that we are reaching our interesting network directly via R3. This is an interesting example of how using multiple tools, such as administrative distance and route filters, you can accomplish optimal routing while also accomplishing reliability and resiliency. Let's move on to our next scenario based on IP SLAs.